and let's get the slideshow set up from the current slide. All right, here we go. Now, that's an example we haven't gotten to yet. That's example 4. So before we get to example 4, I think we left off last time at example 2, but before we get started, any questions on anything we've covered so far? Okay, and let me remind me, I did give y'all the first test, right? Okay, good. Okay. Some people haven't been here to get it, so I don't know what we're going to do. But all right, so let's look at example 2. Here's the integral in question. Whoa, let me get my pen changed back to a darker color. Okay. The integral of sine 4th x cosine 5th x dx. How would you proceed to do that integration? Okay, the sine you said? Okay. Here's the key when you have products of sines and cosines. Hope and pray that one of them's odd. If one of them's odd, go with that one. Okay, so let's fiddle with the cosine. Is that where you were heading, or had you? Okay, so let's do with the cosine. Now, what do we do with the cosine? What do you do with the drunken sailor? Okay, here's the integral. Sine 4th x, and we're going to split this into a cosine 4th x times cosine x dx. And the magic is in the fact that you've now got a cosine x dx. Because that's the derivative of what? Sine. So if you get the other two in terms of sine, you're hunky-dory. Okay? How can you get that cosine 4th to be a sine? Okay. That'll be the integral. The sine 4th x is fine. We're happy with that so far. But that cosine 4th x is really cosine squared x squared, right? And then you have your cosine x dx. Okay. Now, well, I don't have any limits. Why do I start putting limits in? Okay. All right. So the sine 4th x is fine for now. Let's rewrite that cosine squared x as, what were you suggesting? 1 minus sine squared x. Okay. And then we're going to square that and then multiply by cosine x. Not multiply it, we're going to use that. Okay, I don't know how many steps you like to swing this out to, but let's take them all for the first time. You'll find shortcuts later. Sine 4th x. Now let's square that binomial. What does that give you? 1. Okay, isn't that 2 sine squared? Okay, 2 sine squared x. Plus sine to the 4th x times cosine x dx. Okay? Now, I'll multiply through the sines. Okay? That will give me a sine 4th x, which I've had from the beginning, minus 2 sine 6th x plus to the 8th x. Now, my exponent doesn't look very exponential, does it? So let me raise that a little bit. Okay? And all that times cosine x dx. Now, what would you suggest doing now? Say again? Substitution. I like it. What would you substitute? Let u equal sine x, then du is equal to cosine x, dx, write it differentially, okay? And what do we have then? U to the fourth, U to the sixth, U to the eighth, du. And I think that even I might be able to do that one. What would that become? U to the fifth over 5. Got it. What's that? Plus C. Good. We need that plus C. And now what do we do? Plug it in back to what we had before, and this will produce u is sine x, so that'll be 1/5 sine 5th x minus 2/7 sine 7th x. Wait. Let me, got a little sloppy there. Sine to the 7th times x, sine of x to the 7th power, that's what that is, plus 1/9 sine to the 9th power of x plus c. All right, hopefully they got it too. Let's see what they came up with. Sine 5th x over 5, I put it 1/5, it doesn't matter, minus 2 sine 7th over 7, plus 9 sine 9th over 9, plus c. Fantastic. Any questions? Make sense? All right. Now, what did I say our hope and prayer usually was? That one of those will be odd. If it is, we're okay. If it isn't, we're still okay, but we got a little more work to do. Okay? And this next example is the simplest, even only you could have. The integral of sine squared x dx. Now, I was almost under the impression we've already done that. But since they're giving it to us again, okay, you have to dig a little deeper for a trig identity here, depending on how well you learned your trig. And let me see if I can recall in the book where your trig stuff is. I think it's in the back, not in the front. Nope. The heavy cardstock inside. Oh, y'all don't have your books, do you? Inside, in your text, you'll have some fundamental identities there. Most of those are the ones we know really, really, really well. Okay? But when you get down to the double angle formulas, okay, now I can show you how to derive this if you want to see that, and if that helps you, or I can just give it to you. Which way would you prefer? Not? Huh?
I've seen the double angle formula before. It's probably best.
See it? Okay. Let's do it. Like I said, if you had your books, you could look it up. But here's where we start on most of these, especially if you have squareds of sines. Start with this one. Sine squared x plus cosine squared x. And what is that equal to? 1. Always an identity. Now, here's the question. Do you remember what cosine of, say, alpha plus beta is? You remember that one? I'll give you both of them just in case you ever need them. Sine of alpha plus beta, or you can name them anything you want to. I'll just keep from using x's and y's. That would be sine alpha sine beta. No, I'm sorry, sine alpha cosine beta. I'm doing the wrong one. Okay, sine alpha cosine beta plus cosine alpha sine beta.
Oh, yeah.
All right.
Yeah.
Okay. How about cosine alpha plus beta? You remember that one?
I was saying, I don't remember.
Cosine alpha cosine beta minus sine alpha sine beta. Ring a bell? Okay. Now, what if alpha and beta are the same? Then that makes this cosine 2 alpha, or 2 beta, it doesn't matter which one you want, okay? And that would be what? Cosine squared alpha, because alpha and beta are the same, minus sine squared alpha, okay? All right, now, I'm going to rewrite the identity up there at the top, the real famous one, sine squared plus cosine squared is equal to 1. I'm rewriting it this way. 1 is equal to cosine squared. Let me go and put alpha in, since I'd used alpha before, plus sine squared alpha, right? Okay. Now, I wish I had that on top. I wish it were on the bottom. So let me back up. No, let's leave it there. Okay. What I'm going to do is subtract the top equation from the bottom equation. Okay? That would be 1 minus cosine 2 alpha. And when I subtract these, the cosine squareds go out. They've been dating. No, I'm sorry. Okay. And this would become, subtracting the top from the bottom, 2 sine squared alpha. And one more simple little step, divide by 2. Okay? And that would give me sine squared x is the same as the integral of, I'm going to pull the 1/2 out front, okay? 1 minus cosine 2x dx. Wouldn't you say that's a fair swap? Sine squared alpha is 1 minus cosine 2 alpha over 2. So I'll take the 1/2 on the outside and leave the 1 minus 2. Since that's an x, we'll do x dx. Now I think we could probably integrate that one. Can't we? Okay, what would that be? I'll put the 1/2 out front. X minus over a 2, exactly. Okay? And I think you didn't have a plus C, wouldn't you? Okay, if we want to clean that up a little bit, be 1/2 x, or x over 2, minus sine 2x over 4 plus c. Okay, now that's one way to express the answer. Okay, x over 2, I said 1/2 x, minus sine 2x over 4 plus c. That's exactly what we got. Okay, now, as I said before, I was almost certain we've run into that before, but maybe not. We certainly aren't running into it on the slide set here. What's that? Yeah, we did that. I was just going back to make sure I hadn't skipped over it. And when I did it, I thought, well, what happens if we put a 2 in here? We get a minus 1 over 2 sine to the first, okay, x cosine x, okay, plus 1 over 2, and sine to the 2 minus 2 would be 1, okay, I mean, it would be 0, okay. Sine to the 0th, which would be 1, that interval would be x, and that's multiplied by 1/2, so there's your 1/2 x, minus, now here's the problem, it doesn't quite look right, minus sine x cosine x, okay? We didn't get that, okay? So this answer gave us, when we did the integral of sine squared x dx, using this formula, that gave us minus 1 over 2 sine x cosine x plus 1 over 2 x, right? Okay. Now, let's go back to this one, okay? What happens to that if alpha is equal to beta? Then you have sine of 2 alpha is equal to 2 sine alpha cosine alpha, right? Because that would be sine alpha cosine alpha plus cosine alpha sine alpha, that's 2 of them. Okay? Okay? Now, what we could do here is divide both sides by 2. Okay? And that gives you 1/2 of sine 2 alpha. Okay? Let's go back here. Oh, wait. Why did I do that? Let's see. I didn't need to do that. Sorry about that. No, I did need to do it. In fact, I need to divide by 2 again and make this 4. Okay? Now I have sine alpha cosine alpha over 2 is equal to sine 2 alpha over 4, right? Here I have sine x cosine, so this would be minus sine 2x over 4. And if we go back here, there's our answer there. Here's our answer here. Wait. Yeah. 1/2 x, or x over 2, minus sine 2 alpha over 2x over 4. Same answer. Okay. So they used the double angle twice. This answer gave us, in terms of the double angle, the other side of that upper one gave us in terms of single angles. So they did give us their same results. Okay. Now, let's, all right, to clear the ink here. Okay. This is the next example. Evaluate integral of sine 4th x dx. Now, unfortunately, well, sorry about this. What they did, what I think they did here, I mean, they just gave you the answer, okay, or almost. They got you halfway there. What they did here was use, so let's just go back. We can do this, Now you can, I hit the wrong key. What we can do is use this reduction formula. We also call it a recursive formula, whatever you want to do with it. And since we have already had it, and in this text we had it in the previous section, wasn't it? If you go to back to page, you don't have your books, 376, there's the reduction formula for sine nx, and then lower in the page for cosine nx. Okay, so they've already been given to you, so that's what they're suggesting you use. And by the way, let me make sure they give them in the same forms here. It's the same text with different additions. Yeah, precisely the same for sine and cosine. We did those last time. So let's pick up from there and do the sine fourth x. So according to this, the integral of sine fourth x dx would be what? Minus, using this form here, 1 over 4 sine cubed x cosine x plus 3 over 4 integral sine squared x dx. Okay? Only little issue here is we just did that. So this will be minus 1/4 sine cubed x cosine x plus 3/4 of, we just did that at the top part of the page, and that gave us an answer of x over 2 minus sine 2x over 4. And then we had a plus c there before, but let's just go on and close this out and just do a plus c for all of it so you don't have your fractions entering the plus c there. Okay? Now, here's the only issue. Whether you want double angles or single angles, okay? Here we have single angles, and there we have double angles. And you can be happy with either one. Yeah, and I think they stick with the double angles. So let's do it. Okay, negative 1/4 sine cubed x cosine x plus, and what do you get there? 3/8 x minus what's that? Okay, I was going to distribute it in 3/16 sine 2x plus c. Okay, now that's one rendition of it. But that has a 2x in it. Okay, so if you don't like that rendition of it, I thought that's how they were going to leave it. They've done it a completely different way, which is fine. There's nothing wrong with how they did it. But let's see if we come up with the same answer using this way. Again, let's remind ourselves, do you recall what sine of 2x was? 2 sine x cosine x. Remember that? Right. We had alphas before, but that's what it came out. So now let's plug that in here. be minus 1/4 sine cubed x cosine x plus 3/8 x minus the 3/16 is going to be here, but you're going to be inside the parentheses is going to be a 2, so that'll make it a 3/8 also, and then the sine 2 will become sine x cosine x plus c. That is the answer they have here. Not quite in the same order, but close enough. Minus 1/4 sine cubed x cosine x. Then they do the minus 3/8 sine x cosine x. Then they go back and do the plus 3/8 x, and then they do the plus c. So yeah, this gives you the same answer. Now they did it a slightly different way, which is perfectly fine. But man, since you've already got the reduction formula, why not use it? Okay. Their way got you there as well, but it basically dealt with double angles a bit more, and then you were squaring them, fourthing them, and stuff. So it took a bit more to get there. You've got this already. Use it. All right. Now those are the situations when you have an even power of either sine or cosine. Use these formula, reduction formula. But what if you have a product of even signs only? Again, if one is an odd, go for it. It doesn't matter which. If both are odd, you choose. Okay. But if only one's odd, if none are odd, if both are even, and you have a product of sines and cosines, you have another deal to go. Okay. Now, in your text, there's a little side note here, marginal note here. Oh, I hadn't even noticed this. Okay. I was turning back to the front of the book. But in your, if you've got a book, y'all have books, just didn't bring it. Okay, all right.
It's loose leaf.
What's that?
It's a loose leaf book.
Yeah. Okay, right. Yeah, they sell the binders if you wanted to have the binders downstairs. Okay. They have a reminder here of what sine squared is in terms of 1/2, 1 minus cosine 2x. Cosine squared is 1/2, 1 plus cosine 2x. Sine 2x is 2 sine x cosine x, and cosine 2x is cosine squared minus sine squared. So it was all there in the margin. I didn't even look. All right. And then they also have in the margin later down the page what we've just done. Integrating sine mx cosine nx. Well, if either one of those is odd, then we've already dealt with how to do it. But if both are even, which is the case, the next one we're going to do, if both is even, either use the double angle formulas repeatedly or convert the integrand into expression entirely in terms of sine or cosine, and then apply the reduction formulas. So you have two choices there. Okay? So let's take a look at example 5. Now this isn't example 5, that's the one we just did. And there's the one we did earlier, okay? The order is not all that impressive. There's the one we did earlier. Okay? Except this is in terms of single x's rather than double x's, double angle formula. And there's the one for cosine squared. And I think this may be the example. Yes. Evaluate sine squared x cosine fourth x dx. Okay. I'll blow it up to begin with, but when I go to write on it, it's going to have to go back to this original size. All right. If both of these are even, okay, their second suggestion was they said either use the double angle formulas repeatedly or convert the integrand into expression entirely in terms of sines and cosine, and then apply the reduction formulas. Okay? So what they chose to do, since this is sine squared x, I can express that in terms of cosine squared x, and then everything will be in terms of cosine. So that would be cosine 4th x minus cosine 6th x. Use the reduction formula here, use the reduction formula there. You got it done. Okay? Now, let's do it in that order. Okay? We did sine 4th, but we haven't done cosine 4th, so it's probably a good idea to do it. You want to go back to the formula and do it on that page, or do it here? Go back? Okay. There it is. So let's clear this out of the way. Okay. So we're doing cosine 4th x. So the integral of cosine 4th x dx is equal to what? No, that sign is negative. Cosine is positive. 1 over 4 cubed x sine x plus 3 over 4 okay. Now, if you don't mind, let's advance a couple of slides. There was your cosine squared x. Okay? So let's take this. Okay, now, do we want it in double angles or single angles? They come up with single angles, so let's do that. So we're going to use this one right here. X over 2 plus 1/2 sine x cosine x plus c. Okay, so this part here is x over 2. Was it minus or plus? Plus. What was it? 1/2 sine x cosine x plus c. Okay. Now that's going to be the same plus c, so that's completely outside everything here. Okay, so this is all going to be multiplied by 3/4. Okay, so this part here is going to be the integral of cosine 4th x dx is equal to 1/4 cosine cubed x sine x plus 3/4 times x over 2. Wait. Why don't we just, I think that would be better to go on and distribute, don't you? Okay, let's go on and distribute. That will be 3/8 x plus 3/8 sine x cosine x plus c. Word. As I was saying earlier, I crammed down as much salad as I could. I didn't even get halfway through it. Well, what I didn't do while I was doing that was I didn't drink anything, and now that's coming back. My throat feels like it's totally dry, so I may have to, in a bit, take a break and go get some water, but it won't take me long. But let's see if we can finish this one first. Okay? So let's remind ourselves where we were, if I can find where we were. Was this it? Yeah, that was it. So we had cosine fourth x minus the integral of cosine sixth x. Okay. So let's go back and pick up what the cosine fourth x was. That's it right here. That's it there. 1/4 cosine cubed x sine x plus 3/8 x plus 3/8 sine x cosine x plus c. Okay? Whoops. So this is, did y'all get that? No, okay. Meaning when I was reading it, okay. 1/4 cosine cubed x sine x. Let's go back and get that part written in. 1/4 cosine, is that what you said? Cubed x sine x. And I was pretty sure it's a plus, and was it 3/8? 3/8 x plus 3/8 sine x cosine x plus c. Go back and make sure I did get all the pieces right. 1/4 cosine cubed sine 3/8 x, 3/8 sine x cosine x. Yeah, got it. Okay. Now, then we're going to subtract from that cosine 6x. So let's go back and do cosine 6x. The integral of cosine 6x dx is equal to what? 1/6 fifth x sine x plus 5/6. Say that again. Not sine. Cosine. Cosine fourth x dx. Time out again. Okay. So start over here. That's 1/6 cosine fifth x sine x. It is a 5 there. Plus 5/6. Wait, didn't we? No. Oh, guess we did we? Yeah, we're fine. But cosine fourth x we got right down here. So rather than redo it, just write it in. 1/4 cosine cubed x sine x plus 3/8 x plus 3/8 sine x cosine x. I'm going to wait till the very end and put the plus c at the end of all of them. Okay? Is that all right with you? Okay. Oh, man. So let's write out what this finally is. 1/6 cosine fifth x sine x plus 5/24 cosine cubed x sine x plus, now here, that would be 5/16 x. You see what I did there? Okay. Plus 5/16 sine x cosine x. And we'll do a plus c at the very, 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 very end. Okay. Now, but I wanted to remind you that what we're looking for, okay, what we're looking for, let's go back and see it. This is this thing, cosine fourth x minus cosine sixth x. We got them both written back there. I only wrote this one here. Let's go back there. I know we don't have a lot of room, but we can handle it. So it's the cosine fourth x. I'll say we can handle it. Here's the cosine fourth x. 1/4 cosine cubed x sine x plus 3/8 x plus 3/8 sine x cosine x, okay, minus your cosine 6x, right? Here's your cosine 6x. So that's going to be a minus 1/6 cosine 5th x sine x minus 5/24 cosine cubed x sine x minus 5/16 x minus 5/16 sine x cosine x plus c. Okay, somewhere down there. Ran completely out of room. Okay. So, if it's all right with you, I'm going to go back to the top of the page and erase the first two lines. Is that all right? Hopefully, I haven't made a dumb mistake there that I'll need to recreate. If so, I'll leave that for you to investigate at home. Is that what math teachers usually do? Okay, I thought so. Okay, I want to be a good math teacher, so the rest is left to the student, you know, if I screw something up. Figure out what it is and correct it. Okay. All right. So let's see what we can do with that. I'm not going to write the problem down, but it's this right here. So say, here we have a cosine cubed sine. Here we have a cosine cubed sine. The starting out with a 1/4 minus a 5/24. 1/4 is 6/24, right? Minus 5/24, that should be 1/24 cosine cubed x sine x. Okay? Here we have a 3/8 x and a minus 5/16 x. Well, 3/8 is 6/16 minus 5/16 would be a plus 1/16 x. By that? Okay. And here we have a sine x cosine x, a 3/8 sine x cosine x, and here we have a 5/16. So again, that 6/16 minus 5/16 is a plus 1/16 sine x cosine x. Okay, so these are done. These are done. These are done. And all we got left is a minus 1/6 cosine 5th x sine x and a plus c. Now, that's one way to express it. I sure hope they don't want us to factor out greatest common, something with the denominators. Let's see what they get as their answer. Okay. If I can find their answer, there it is. They start with the minus 1/6 cosine 5th x sine x. Bingo. Got it. Okay. Plus 1/24 cosine cubed sine x plus 1/16 cosine x sine x. Okay. Plus 1/16 x plus c. Very good. They wrote it in a different order, and for some strange reason wrote the cosines before sines. It doesn't matter. Oh yeah, they did on the first two, so they did on the last one too. It doesn't matter. Okay. So, since these are recursive formulas, recurse them as much as you can. To take advantage of, when you get one thing here and it shows up somewhere else, plug it back in. Okay. Let's move on to example 6, if we can find example 6. Oh, they also wrote it with the double and four angle and 6 angle formula. And there your denominators get far, 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 far worse. So I kind of like them the way we did it. Okay. So let me see if I can find where we were. There. That's the one we just finished. Okay, this is filling in the gaps here. Oh, is that our final answer? I think it is. Yeah, that's it. In the order they did it. And just to blow this up a little bit, if we can get it all to, well, why is it being so stubborn? Okay, here we go. All right. How they wrote it, and I just read the answer to you, they do it in decreasing order of the cosines. Cosine fifth, third, first, and just let everything else hang on. That's why they started with the minus. I don't like starting with minus, but that's fine. Minus 1/6 cosine fifth sine, plus 1/24 cosine cubed sine, plus 1/16 cosine sine. That's why they did that, I think. And plus 1/60 x. In case you couldn't read my ugly scratch, there is the thing. All right. That's a completely more complicated problem. That is our example. No, it isn't. That's our example. No, it isn't. It's not any of the examples we have here. Okay? It's close to some of them, but not the same. Okay? I don't know if we'll come back and do that or not. But what we're doing next is integrals of tangents and secants. Okay? And where you have to begin, and there's a little note here, the integral of secant x dx was first computed numerically, if you can believe that, numerically, in 1590s by the English mathematician Edward Wright. Talk about method of exhaustion. Okay. Before the invention of calculus was even there, he had come up with that. Although he did not invent the concept of an integral, Wright realized that the sums were that approximate the integral hold the key to understanding the Mercator map projection. So far, I haven't been able to establish in my mind the connections here, but he did it, okay? I guess they use secants there. Of great importance in sea navigation because it enabled sailors to reach their destinations along lines of fixed compass direction. The formula for the integral was first proved by James Gregory in 1668, so about 78 years later. Okay, so there's a couple of people that you could write on, and the thing with the Mercator map, how calculus relates to that. There's several other potential paper topics. Okay, enough of that. Let's move on. Now let me make sure they don't have this done somewhere else. No, I don't think so. All right, we'll do it on this slide even though we're not doing that slide. It says derive these formulas. The integral of tangent x dx. Where would you begin to come up with an integral of tangent x dx? Fantastic. If I have a problem in trigonometry that I can't see an answer to, I'm going to try to get everything in terms of sines and cosines. So that integral would then be the integral of sine x over cosine x dx. Okay? Now, where would you go from there? Okay, pick a u substitution. Okay, let u equal what? Would say again? Okay. You're asking me, okay. I go for the most complicated part of the problem, the simplest form in that. Well, the most complicated part to me there is the denominator. Simplest, well, the only thing there is cosine, so let that be our u. Let u equal cosine x. Then du is equal to negative sine x dx. You know, I'm okay with that. We'll just move the negative over here in front of the du. So we got our sine x dx right where we want it, and we got our u. So that's our negative du. So this is minus the integral of u du. Right? All right. Can you integrate that? Say that one more time. No? You're right. Yeah, I'm sorry. 1 over u. Yeah. Can you integrate that? Minus log u. Actually, you should put that in absolute values because you can't ever take the log of a 0 or a negative. Okay? So that's now plug back in. Of, cosine x. And we'll put that in absolute value bars too. And I'll go on and put my plus c out here. Okay? Now, little bit of a quiz here. Do you remember enough about log functions of a rule of what you do if you have a coefficient in front of the log function? Exponent of what's inside. So this is the same as the log of absolute value cosine x to the minus 1, which is the log of 1 over cosine x plus c. Now, quit doing the absolute values, but we could. Okay. And this is, what is 1 over cosine? Secant. So this is the log of absolute value secant x. Sometimes my secant x has come out sex, and that's not very good. Secant x plus c. And we've just done what they ask us to do, derive that formula for integral of tangent x. The log of absolute value secant x plus c. Okay? Now, talk about a big boo hiss. They want us to do the same thing for secant x. Okay? And I'm going to have to erase. Y'all got it, though, right? Okay. We're going to do the integral of secant x dx. Okay. I wish it were that nice. Okay. There's a trick here. And we could spend all day trying to figure out how to rationalize the trick. It's a lot easier just for me to tell you the trick. Okay? And here's the trick. Of course, it's the first thing I would have thought of doing is rewriting this as the integral of secant x times secant x plus tangent x over secant x plus tangent x. Well, what's that ratio equal to? 1. So we can multiply by 1 anytime we want to, right? And this is dx. Okay. He may need to see me, so I'm going to pause just a second. Might do next. Let's distribute the secant in the numerator. The integral of secant squared x plus secant x, I did it again, secant x tangent x over secant x plus tangent x dx. All right. Yay, that looks a lot better, doesn't it? All right. Anyone want to hazard a guess what we might do next? What you might notice? Well, based on what we did before, and I was not as far back as taking sines and cosines. We were already past that. But what did we do before when we had something in the denominator? So, yeah, substitute. Let that be our u. That's a stretch, isn't it? Let u equal secant x plus tangent x. This is the magic. Then what? Du is equal to wait. Okay, I don't know why. Okay. What's the derivative of secant x? Secant x tangent x. What's the derivative of tangent x? You just said it. Secant squared x dx. And guess what we've got in the numerator? We've got our du. So again, the integral is just like before, the integral of du over u. How does that integrate? Just like before. Log of u, absolute value. I'll put the plus c in there. And then let's plug in what u is. The log of secant x plus tangent x plus c. There we've done it. We've derived the second one. The integral of secant x dx is the log of secant, the absolute value of secant x plus tangent x plus c. I don't think in a million years, well, maybe less than a million years or something, I would have thought, why don't we do that? You know, it's just a trick. Now, I think we probably could have gotten there with sines and cosines, but it would have been a long and tortuous route with a lot of insight. This just happens, if you do that, you eliminate a lot of pain. Okay? So that's their hint. They had us do it. It worked. Okay? Now, with those hats in hand, let's use, well, basically, now that they've had you do all that, they say, you know, what's a lot easier is using a table of integrals. Okay? Because guess what? The tables have those recursive relationships. They have those reduction relations. They have these. They have everything you need. Why reinvent the wheel? Use the table. Now, I can remember seems like it was when I was in my physics sequence. I was a physics major, and it was a junior physics sequence, I think it was, when, you know, that was one of the hardest sequences. That it was, what, 301, 302, 303, I believe it was. I was on the quarter system back then. It was the dread, you know, of everyone who's a physics major, because that really got deep. The sophomore level physics, everybody took, engineers, you know, and everybody else. Boy, when that was the one that the physicists, and generally made or broke physics. You know, if you could get through that, you could get your degree. If you couldn't, find something else and do it. But, so anyway, I believe it was the first term of that. Dr. Young, I think I'm pretty sure was my professor for that. And I don't know why he did it, but he came in one day and said, if y'all don't have one of these, you need one. It's a huge, thick book, and it was, I just had the name on it. It's the CRC handbook. Have you seen her? Okay. The CRC handbook, and CRC stood for Chemical Rubber Company, but I don't know if the company ever existed anymore. It probably did, but the handbook was a life of its own. And it was for physics and chemistry. And it was a big, thick, I've got it in my office downstairs, about that thick, about that tall, that wide. And the paper was the finest, thinnest not newsprint. I mean, you could almost see through the pages, it was that thin. So it had well over 1,000 pages in that. And in the math section, literally page after page after page after page of derivatives, and in small print too, on and of integration. And boy, that still lives with me. Okay, that's what people use. Nowadays, of course, you have the internet. Back then, we didn't. We just had gotten slide rules in. I was just telling my last class, I saw my first calculator, my first quarter of my sophomore year in college. And it could add, subtract, multiply, and divide. And guess how much it cost? Huh? $700, you said? I think these were $600. Okay, $600. Wow. Now, within months, the price was falling like crazy. But those first what it was 8 o'clock, first day of class, Monday morning, I guess, whatever morning it was. It's a physics lecture hall. This is sophomore physics. 200 plus students in there, and in walked two with this thing on the belt, and the rest of us said, there goes the curve, because they could do it so much faster and more precisely than we could with our slide rules, because everybody had a slide rule. And we said, there went the curve, and then we found out $600. They were, I think, HPs, and within a year, TI was out and making them much cheaper. HP prices came down some, and then they started picking up more functions. But still, at the time, you had to plug it into a wall. They didn't have enough battery power to do without the wall. And then in a few generations, they were able to keep a charge for a class or two, and the rest is history. But so back then, CRC handbook, that was equivalent to our internet. Okay, are both of you engineers? Okay, I know at some point you'll be taking. Do they call it the EIT or pre-engineer or PPE or something? Is that what it's called? Huh?
The FE and the P for like professional engineering.
Okay, what's the FE stand for?
Fundamental engineering.
Okay, it used to be called the EIT, Engineering Training. Okay, that's the first series you do of test after you graduate, or you might actually do it while you're still in
I
school.
think you can do it maybe at the end of your junior year.
Yeah, okay.
Yeah, I think you have to work under a professional
Engineer for a while before you take the PE. I was physics, so I didn't have to do that, but Georgia Tech, most people were engineers, so everybody was sweating the EIT. My younger brother went to the University of Georgia, and he did the PE, his PE in electrical, so, and he sweated that too. Everybody sweats. But then, back then, you carried in stacks of books, and odds are CRC handbook may have been in that stack. Mostly they were engineering texts, but
I think they still have to bring
source. Okay, even though people have calculators and phones, they can call up anything they want to, or
I don't
pads.
think you can have it.
Oh, you can. Oh, so then you do bring in your book. Okay, that makes
I
sense.
know I was talking to a guy, the she graduated early 2000s, and they said when he took his PE, he had a whole,
Yeah.
what's it called, hand truck.
Yeah. And you better have a pretty good idea where you to look and all those things, so you don't have time to thumb through the index, you know. So, yeah. So they still do some things the hard way, the old way. Okay. So let's go on and clear this. Sorry, that was somewhat of a distraction, but using the point was tables of integrals. This has 19 here. You turn to the back of the book if you got your book text. I don't even think they number them. Well, they're somewhere back here. Here they. Yeah, they got 111. The CRC handbook probably had several hundred to 1,000 or so. I mean, so you can get tables that'll do just about everything you need. And then in reality, if that wasn't bad enough, there's some integrals you're not going to find in any table at all. You do those numerically. So you buy packages that do them for you. So after a while, especially you engineers, you're not going to do this anymore. You're going to go to something else. But anyway, we're here now, so let's do it. Off my badge. Okay. Now this may be the first definite integral we've hit, I know, in quite a while. I think maybe the whole section. 0 to pi fourths of tangent cubed x dx. Okay? Now, we did tangent. We didn't do tangent cubed. Okay? So, there is a side note here, a marginal note, that talks about tangent m secant n. Okay? And again, the first and the easiest case is that m is odd. Oh, well, that one of them, well, no, especially the tangent is odd. M is odd. And n greater than or equal to 1. Okay? That would be the case here, except n's not greater than or equal to 1. So it's not the case. Second case, n even. Well, n is a secant. It's 0, but that's not going to help us there any. In the third case, m is even and n is odd. That doesn't fit because the m is the one for tangent and the n is the secant. So that's not going to help us here. So basically here, we got to go to the table. Okay? And here in the table, and if you don't have the table, here it is. I'm going to give you the generic first. Well, I'll give you what table says. I'll write the table down here. The integral of tangent to the nth x dx is equal to the tangent m minus 1 x over m minus 1 minus the integral of tangent to the m minus 2 of x dx. All right. There's what the table says. Apply it up there. What would that give you? Tangent squared x over 2. Now, since we have limits on this, we're going to evaluate that from 0 to pi fourths. Okay? Sorry. Okay? Minus the integral of tangent. And that's from 0 to pi fourths. Okay? X dx. Okay? Now, time out. What if this had been from 0 3/4 pi. Okay. Here's what you do. Picture your tangent function. How does it look? And then, okay, vertical asymptote square. Minus pi over 2 to the pi over 2. Can't do it if that was 3/4 pi. You cross a vertical asymptote. Trick question, okay?
Yeah.
So looking at this, perfectly fine. Tangent is defined well within these, 0 to pi/4. So yeah, no sweat there. We can do it. So you can only integrate things that are continuous. Okay, tangent is not out, but out if it crosses pi halves. Okay, so what does this come out being? Okay, wait. No, do the evaluate the tangent. What's that?
I wasn't looking at the square.
Yeah.
Tangent square
What is tangent of pi over 4? 1. And 1 squared is 1, and 1 over 2 is 1/2. Okay, minus at 0. What's tangent at 0? That is 0. So you got that first part done. Thank you very much. Okay, now we do the next part. And what did that one? You were saying it? Absolute value secant x. Okay, and that's evaluated from 0 to pi/4. And actually, picture your secant function. What does it look like? This what? No, that's the inverse tangent. Secant, remember secant and cosecant basically, okay, picture a sine and a cosine.
Does that take bump from the top or the bottom?
Yeah, they are up here and down here, up here and down here. Yeah, that's it. And from 0 to pi/4, that's positive. Okay, so you can lose the absolute value sign because you're within the place where it's all positive. So I will do that just so it won't be there anymore. Okay, and with that in mind, maybe a little bit easier to do would be 1/2 minus the log of, and since you're in the first quadrant, everything's positive, the log of 1 over cosine, because that's what secant is, okay, between 0 and pi/4. Okay, now, anyone remember what cosine of pi/4 is? It's a weird number, right? Okay, 0.707. Yeah, okay. That's square root of 2 over 2. Okay, pi/4. Okay, it's cosine of pi/4. Okay, so this would be minus the log of 1 over the square root of 2 over 2. Well, wait a minute. What is, okay, let's back off here a minute. Square root of 2 over 2, another way to write that is 1 over root 2, right? Rationalize that denominator and you get that, right? So 1 over root 2 would simply be root 2, right? So that'll be a lot easier to write it that way. Log of the square root of 2. Okay? Which actually, I don't know, I think so, would be log of 2 to the 1/2, which may be the easier way to write that then, would be, well, wait, 1/2 log 2, Remember that same rule of logarithms we were talking about before? Okay, that looks nicer anyway. I don't like radicals. They're ugly. Okay. Okay, so that's the first entry. What is cosine of? And then you've got to have another minus here. The natural log of, and what is cosine of 0? One. And 1 over 1 is 1. And what's log of 1? 0. Oh, yeah. Log of 1, which is 0. Okay, so that's the end of it right there. So your answer then is 1/2 minus 1/2 log 2. Now, if you want to plug that in and see what the value is, they left it as minus log square root of 2. You could do it one. Okay. So they left it in what I had before, like that. Doesn't matter. There's your answer. Okay. Got it? Now, let's go to any questions on that before I erase it. Okay. So let me erase all those and go to example 8. Evaluate this one. The integral of tangent cubed x secant fifth x dx. Okay. Now this is one we would use the marginal notes if you're wanting to run through it on your own. So let's take a look and see. Here we have tangent m secant n. Okay. Case 1, and this is usually the easiest case, if m is odd and n greater or equal to 1. Yes, that works on both counts. 3 is odd and 5 is greater than or equal to 1. So this is what we want to do. Okay? Now, it goes back to something we just did, or something close to it anyway. Factor out a tangent secant. Why would we want to do that? Or a secant tangent? That's the derivative of secant. Okay, so that's what we want to do first. That will leave us a tangent squared x secant fourth x times secant x tangent x dx. Okay. So, fine. Now, why was it sort of nice to have, in fact, required for this one, for that tangent to be odd? We're going to factor out a tangent, but what we want then, that what's left to be even, because what can we do with an even tangent? Okay, and what's that relationship? Is what? Yes, that's it. So this is the integral of secant squared x minus 1. I have to go back. Yeah. 1 plus tangent squared is secant squared. Tangent squared is secant squared minus 1. Got it. Times secant fourth x. Okay. And then I'll just leave secant x tangent x dx together. Okay. So this would then be the integral of secant 6x minus secant fourth x times secant x tangent x. And then what would you do? Substitute, and what would be your substitution? Secant x, you got it. Then du is equal to, second, secant x tangent x dx. Now you see why that works so nicely. So this will be the integral of, and by the way, they didn't have limits on this. No, they didn't. Of what? U to the 6 minus u to the 4th du. Perfect. And that would be u to the 7th over 7 minus 5th over 5. And you could put a plus c there if you want to. And then you plug back in, and what do you have? Secant 7th x over 7 minus secant 5th x over 5 plus c. And let's see if that's what they got. That's what they got. Good for them. Okay. Now, the next one they do here in this, in the new edition, is almost like the one they've got here, but not quite. So we'll do the one in our book. Can I go and erase this? Okay. All right. Here's the one. The integral of tangent squared x secant fourth x dx. Okay? Now, obviously case 1, not satisfied. Tangent is not odd, it's even. Case 2, if that n, which is the secant, is even. Yes, that works. Okay? So then we can do case 2. What does case 2 tell us to do? Well, we're focusing on the n being even, so what we're going to do is factor out, and I mean, once you've done a few of these, you sort of see their pattern, factor out a secant squared. Okay? To me, this is the easy one. This should be first case, but they don't do it this way. Okay? So this will be the same as the integral of tangent squared x secant squared x secant squared x dx. Okay? What you reckon we're heading for now? Yeah, not yet. We got to do another step, and then we'll be doing it. But where are we heading to substitute? When you factor out that secant squared, what's secant squared x dx? That's the derivative of? No. Tangent. The derivative of tangent is secant squared. So that's going to be derivative of tangent. So if we can get the others in terms of tangents only, which we can with the secant squared, right? How can we do that? What is secant squared in terms of tangent? Tangent squared plus 1. Okay? We've got it knocked now. So what's our integral now? Well, times that. So that would be tangent fourth x plus tangent squared x times secant squared x dx. Now we're ready for our substitution. Let u equal tangent x, then du is equal to secant squared x dx. That took care of that. So this becomes what? The integral of u to the fourth plus u squared du. Done. And how does that integrate? U to the fifth over 5, u to the third over 3, plus your good old c there. Now you plug back in tangent fifth x over 5 plus tangent third x over 3 plus c. That should be a bingo if we weren't in Alabama. Okay, yes it is. All right. Now, this one comes out of the blue. Okay? And there is, from way back in trig, they had some product to sum formulas and sum to product formulas, right? They weren't worth memorizing in my book, because if I ever needed those babies, I'm going to look them up. Because guess what? I don't trust my memory. Number one, I'm not a memorizer, so I'm not about to trust a memory that I don't memorize well, so I'm going to look it up. And guess what? If you work for me, am I wanting you to, oh, I think it's this? No. Bring in your stack of books. I want you to look it up and make sure you've got the right formula. Okay? So that's where this is coming from. And just don't even, I mean, if you want to have a trig book and look it up, that's fine. But the thing is, this is in your table of integrals. Look them up. Here's the integral. Evaluate from 0 to pi sine fourth x, no, sine of 4x, not fourth x, cosine 3x dx. Now, do I remember what to use it? I remember what to use, but do I remember exactly how to use it? No. I'm going to look it up. Now, if I don't have a table of integrals, I'm going to go to my trig book and look up and see. It's a sum to product, product to sum, something like that. Okay? But guess what? We got a table of integrals on this very page, and number, this is sine, cosine, this is number 18. I'll write down what number 18 is. And this is not everybody's number 18. This is this book's number 18, so don't think. It reminds me of a really dumb joke. You want to hear a dumb joke in the middle of class? Okay. This guy had gotten caught doing something, wound up going to prison. Okay? And of course, he was really scared. He was sort of a youngish kind of guy, and he had heard all these horror stories about what prison was like. He was scared to death. Well, this older prisoner sort of saw how fearful he was, and he sort of took him under his wing and said, "Look, kid, hang around with me, and no harm will come to you. I'll make sure you're okay." So he did, and they went to the cafeteria that first evening, and they were there eating and stuff, and then someone just yelled out, "Number 14!" And they all just burst out laughing. And sometime later in the meal, someone said, "Number 83!" And they just burst out laughing. The kid did not know what was going on. So later that evening, the last walk around the yard before they're going to have lights out, he said, "Hey," to his older protector here, he said, "What was going on at supper?" He said, "Oh, I forgot. You're new here." Yeah. Look, most of us have been here so long, we know all the jokes. So rather than go through the telling the jokes over and over again, we just number them. So we just call out the number, and then people remember what the joke was, and they laugh. So a few days later, the kid was working up a little bit of courage. He wanted to get into the thing. So during the meal, he called out, 23. They just sat there and looked at him. He felt so small. Later, went up to the guy and said, "What did I do wrong?" He said, "Look, kid, Some people can tell a joke and some people can't. All right. So number 18, that's terrible, wasn't it? Okay. Here's what number 18 tells us. Sine of mx cosine nx dx. Here's the integration of it. Minus cosine of m minus n x over 2 times m minus n. Why didn't I memorize this one? I don't know. Minus the cosine of m plus n x over m plus 2 times m plus n plus c. Now what's the requirement here? M cannot equal plus or minus n. That's the only contingency here. If they were the same, you do something else. If they're exactly opposite, do something else. But if they're not the same or opposite, then use this formula. These are not the same, not the opposite, so use the formula. And what would that give us? Minus second, yeah, x, cosine x over 2, yeah, 2 times 1 is 2, okay, minus cosine of what? Second? No. M plus n. 7x over 14. Well, no. This is a definite integral. So we evaluate that between 0 and pi. For some reason my 0 didn't write. Okay? So this will be minus the cosine of pi over 2 minus I'm going to do it this way, minus the cosine of 0, minus a minus, which is plus, over 2, minus the cosine of 7 pi over 14, no, wait, yeah, plus, minus a minus, the cosine of 0 over 14. That seems a little strange to do it that way, but hopefully it'll make some sense. What is the cosine of pi? -1. So it's minus a minus 1, which would be a plus 1, so that'd be a 1/2. Plus, and what's the cosine of 0? 1. So that'll be a 1/2. That's why I did them that way. Okay, minus, the cosine of 7 pi. Okay, don't worry. Hey, think. Okay? 1 pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, -1. So that's also a -1. So that would be a minus 1/14, right? Plus 1/14. That's still a 0, right? Okay, so what does this give you? 1 1/7. Or you could say 8/7. Okay? and that's what they got. Now, are you satisfied just using the table like this, or do you want to know why that's true? Yeah, y'all are good engineers. You don't care why. Okay, right. Okay. In a sense, me either. Okay. There is a way you can go back and do that. All right. Y'all want to do the preliminary exercises? Okay, what? Okay, now they did have here, theirs that wasn't in here. So let's take a look at this. Let me go on and clear this. They took this one out when they changed edition. So let me goodness, I'm so hungry. I've only got half my salad eaten, so I'm starving. Okay. The tangent squared x secant cubed x. What are we going to do with that? If you see here, the first case, m is not odd, it's even. So go to the second case, n is even. No n is odd, because it's secant n. And then case 3, m even, yes, and n odd, yes. Okay? Now, what we do with that, we use the fact that, I've got to, okay, go back. What we do, we use the fact that tangent squared x is equal to, what was that identity again? Secant squared x minus 1. Got it. Okay? So we use that here, and that will then be the integral of secant squared x minus 1 times secant cubed x dx. Okay? Which then would be the integral of secant fifth x minus secant cubed x dx. Okay? Now, there's no substitution we can do to undo that, but there is the recursive or reduction formula that we have, and that's number 14, that tells you that secant, I can't write, the nth x, the integral of that dx is equal to tangent x secant to the m minus 2 x divided by m minus 1. Why don't I memorize these? It would be so easy, wouldn't it? Right. Okay. Plus m minus 2 over m minus 1 times the integral of, make sure I got my signs right, secant m minus 2 x dx. Okay. And that basically is what that's the first step of what they did right there. And then we'll use this form, and this is an indefinite integral, so this one. So we would do this, and then we wind up, and I would start with the secant cube and do what secant cube is. Okay? You'll get an answer for secant cube. Okay? Now, using this formula. Then the secant fifth, when you go to do that, you're going to wind up with an integral for secant cube again. And you've already got your secant cube, so then you plug that in, so you just keep feeding it back in where it needs to be, and ultimately you'll get to your answer. Let's see if they actually do it. They carry it part of the way anyway. Yeah, there's that formula we just had. Tangent x secant Hopefully they're doing just secant. No, they did secant cube. Yeah, well, it works either way. They did the secant fifth part first. Okay. And they skipped so many steps, it's really hard to see. But this is the secant fifth part here. And you see this has a secant cube part in it. And just subtract that out, and then you get to this, and then do your reduction on the secant cube. So you could either do the secant cube first and then plug in, or either way works the same. Okay, let's see if they do. No, they don't do any more. Now, their numbering here is different from the numbering in your text, so don't worry about that. I mean, it's just a series of things. Who cares about the number anyway? But there's your sine squared, cosine squared. We derived both of those. Sine to the mth, cosine to the mth, sine to m, cosine n, sine m, cosine n. And now what you notice here, they look like the same ones, except that you have different conditions on them. And why they didn't put the conditions here, I don't know. Okay. So I think you have to almost go back and see what the side notes, the margin notes were on those. Then you have tangent x, which we derived, tangent mx, cotangent x we didn't do, but it's very similar to tangent. Cotangent mx, secant x we derived, secant mx we've used, okay. Cosine, now cosecant x, very similar to secant, only with with your cofunctions and the sign change. So there are some differences there. Then so keeps cosecant mx, and it's mostly sign changes and cofunctions, but you don't change necessarily all the signs, but you change some of them. So, and then you got your sine mx, sine nx, your sine mx, cosine nx, which we used, and then cosine mx, cosine nx. Okay. So they basically just numbered them differently in your text. Okay. That finishes 7.2, I think. Yeah. So let's see if there's any. Did y'all want to do the preliminary questions? I don't know if y'all do like them right or not. Okay, let's do it. Preliminary question 1. Describe the technique used to evaluate the integral of sine fifth x dx. I can think of a couple answers. What would you say?
Did you break it down into 1 minus cosine squared x
Okay, pretty close.
plus, and then use your sinus and substitute?
Okay, okay, yeah. By the time you got there, I think you got it all set. Pull out a sine x, because that's a derivative of cosine. That leaves you with cosine squared. The cosine squared is cosine fourth. That's a cosine squared squared, and then change the cosine squared. Then expand that, and then do your substitution. That is what I think they were looking for. The other option? Look it up in the paper. Okay, that was the one I was wondering if someone was going to say. Let me make sure that we set. I'm pretty sure we said it right. So let me do this. 7.2 preliminary questions. Rewrite that as a sine times sine fourth, and the sine fourth is 1 minus cosine squared, and then substitute u equal cosine. That's what you were saying. Now, number 2. Describe a way for evaluating this one. the integral of sine 6x dx.
That's the first answer.
What's that?
That's the first answer, which is looking at the table.
Yeah, that's certainly, I think after a while would be all I'd ever do, you know. But the way I think they're wanting you to think of is to do some, write that as sine squared cubed. And sine squared you can write as a double angle formula like we did before. And then you got that cubed, and you keep doing that until you get down to a form. So basically, when you have an even power of this, basically, ultimately comes down using double angle formulas. They don't put the odds, the evens back here, so that's what you do. Or use the table. Yeah. Number 3. Are the reduction formulas needed to evaluate this one? The integral of sine 7th x cosine squared x dx. Do you need to use a reduction formula for that? Why not? Pull out a sine, get it over here, that's the root of the cosine. Take this sine to the 6th as a sine squared cubed, and the sine squared can be written in terms of cosine. That sine is the root of the cosine. Of course, you got a cubic that you have to expand, but you can do that, you know, as a Pascal's triangle, that kind of stuff. So you can do that, and it's fairly straightforward. So no, it's not necessarily to use the reduction formulas, but you still could. No, a reduction formula not needed because the sine function is raised to the odd power, which is what we said. Okay, number 4, that answer is not in the back because they don't, for this section, why, I don't know, they only have the odds. Describe a way of evaluating this one, the integral of sine 6x cosine squared x dx. Second? Possibly you could. I think a little easier than that is just write this as 1 minus sine squared. And then you have that, and then use your reduction formula. The double angle formula, you'd have to use it several times for this and that, and it probably is going to be more trouble than it's worth. But doing this to 1 minus sine squared, and then you have sine 6 minus sine 8, and then just use your reduction. I think that's the easier way to go. Okay? Or look it up at the table. Okay? That's the easiest. Number 5. Which integral requires more work to evaluate? Here's the first one. The integral of sine to the 798th power x cosine x dx, or integral of sine 4th x cosine 4th x dx. Which of those requires more work to evaluate and explain? Say again? Actually, first one's pretty easy. With substitution, u equals sine x. The u equals cosine x dx. U to the 798th power du. That would be.
That makes a lot more sense now.
Huh?
That makes a lot more sense now.
Yeah, but that one will require quite a bit. So the second one does require more work. Even though the numbers are much smaller, they're both even, and that's sort of the pain in the neck. The second integral requires the use of reduction formulas and therefore more work. The other's just really a simple substitution. Even though it's a big exponent, they work the same way small exponents do, so good deal. Homework exercises 7.2. Do any of the odds 1 through 5? Do 7. Do any of the odds 9 through, either 9 or 11 or both. Do number 13. Do either 15 or 17 or both. 19 or 21 or both. And then you have about a passel and a half of these things. Any of the odds 23 to 47. And I would do enough of those so you feel pretty confident about it. Then you got another pretty good big group, 49 to 61. Any of those odds. And then you've got some miscellaneous odds. Do either 63 or 65 or both. And then either 67 or 69 or both. And then any of the odds 71 through 77. Now, I was looking to see if anything, there is something mentioned in number 77. It's talking about orthogonality relationships, but it's specifically in Fourier series. So since they mentioned him there, Fourier would be a pretty good paper topic, or what do his series do for you? In fact, you might even want to get into Fourier analysis. You don't have to get into great detail. It's beyond the scope of this book. But Fourier dealt with sines and cosines like crazy. And basically, functions that are almost impossible to do otherwise, he could solve with a Fourier series to pretty good accuracy. And so you can take a look at that as a paper topic if you haven't chosen one already. All right, now those were trigonometric integrals is what they were called. This next section, which is called, don't get them confused, they're fairly separate. They are separate, they're different. Let me get the thing to 7.3. This is trigonometric substitutions as opposed to trigonometric integrals. This morning it had a hard time loading the PowerPoint and acting almost the same way, but let's do it a bit better. This morning it would sit there and vibrate a little bit and then nothing would happen. And okay. I don't know. It could be. It's old enough. Sounds like another dumb joke, but probably I shouldn't go there. Okay. Not exactly the same way this one starts off. It is close enough. Oh yeah, it kind of gets there after a bit. Before I get down to the specifics, let me start a bit more the way the new edition does. Whenever you have a form, let's just make sure they don't have this later. No, okay. Whenever you have a form, how we doing? Okay, I've got plenty of time. Whenever you have a form that looks something like this, the square root of a squared minus x squared, the square root of x squared plus a squared, and by the way, that could be a squared plus x squared, it doesn't really matter, or the square root of x squared minus a squared. Okay? These could be in numerators and denominators, anywhere in a problem. Then probably a trig substitution is going to be your key to solving that. Now, certainly, if you had somewhere a 2x, like in the numerator here, that's a substitution right off the top. But if you have these without having a derivative somewhere else in the problem, then these can be a pain in the neck. Okay? So what you look for then is a trig substitution. And which one and how we'll talk about. And frankly, I really don't know if I should do this because this is how my weird mind works. And I'm not wanting to impose that on you. But the first one, I think sine or cosine, and the main reason is because sine squared, okay, number one. If you got squareds in there, think Pythagorean identities of trig functions, right? And since a sine squared is 1 minus cosine squared, or a cosine squared is 1 minus sine squared, that looks a lot like this to me, right? Now, tangent squared plus 1 is a secant squared, so this looks like tangent substitution would be good. X squared minus a squared, that looks a lot like your secant squared minus 1. That's going to be a tangent square, so secant would be your good. So I look at them that way, and as soon as I do, that sort of gives me a real good feeling that's the way to go on this. Okay? And they start off with this one, and they point out to you if you make the substitution, and they just sort of say, do this and it works. See? Well, I look at it and say, that looks like something that looks familiar. Let x equal a sine theta. That's the substitution. Well, let's see what happens. This x isn't x, it's squared, so then x squared is equal to a squared sine squared theta. Okay? And then if you put that in there, you have the square root of a squared minus a squared sine squared theta. Well, guess what? You can factor out an a squared. And that will just leave you an a outside the radical, 1 minus sine squared theta. And what's 1 minus sine squared theta? Cosine squared theta, and then the square root of that would be a cosine theta. And that we can deal with, wherever it is, numerator, denominator, whatever. Usually we have a better chance of dealing with that. Okay? Now, with one exception. You have to kind of put some limits on this. Because remember, sines and cosines are repeating functions. So let's keep sine theta so it's not backing up on itself anywhere. In other words, keep it 1 to 1, and that's going to work from theta minus pi halves to pi halves. So that's usually the limits we'll put there. Okay? Because later we might need to do an inverse function to get out of it, and you've got to be places where those are defined. Okay. So with that in mind, let's do example 1. So let's clear this. Man, I am so hungry. I think my stomach's devouring my liver right now, but we'll see. Okay. Here's what we want to evaluate. The integral of 1 over the square root of 1 minus x squared dx. How would you approach that? a let u equal substitution, not going to work because you have to have a 2x in that numerator. What's that? Not tangent. Tangent, you know, appear at 1 plus tangent. Yes, correct. You could do cosine or sine. I think the book likes to usually do sines. Yeah, they do that. And since there's the a is 1, we'll just do let x equal sine theta. Now, notice what's different from here in our previous substitutions. The previous substitution, we'd pick out the complicated form and let u be that form, right? This time, we're taking the variable that's given and let that be a trig function, okay? So it's kind of a different kind of substitution. It is a substitution, but it's not a new variable equaling some form that you have in the problem. It's the variable in the problem equaling some trig form, okay? So let's carry through and do what we had done before. There's a couple things we've got to do. A couple of thens here. You tell me one then that we got to do. Second? Let's do our dx. Dx is equal to cosine theta, d theta. Perfect. Another couple things you might want to do. Again, from the top one. How about x squared? X squared is equal to sine squared theta. Then 1 minus x squared is equal to, you got it, cosine squared theta. And then that would produce the square root of 1 minus x squared would be cosine theta. Now, if you're limiting yourself to minus pi halves to pi halves, which we suggested before, this is perfectly fine. Because minus pi halves is to 0 would be fourth quadrant, and 0 to pi halves would be first quadrant. So minus pi halves to pi halves are the two quadrants for cosine is always positive, so you don't need to worry about plus or minus here. So they're always going to be positive. So that's the other reason for that. So now that we've done all that, what's our new integral? You got it. The dx is cosine theta d theta. That's in the numerator, and your denominator, that's cosine theta. Boy, I think I like this one, don't you? What did that result in? Theta. And you could do a plus c if you wanted to. But now we got to go backwards. Okay? And if sine theta is equal to x, then another then you got here, theta is equal to inverse sine of x. Okay, take the inverse sine of both sides. Okay? So this is going to equal the inverse sine. Goodness gracious, I say inverse and write a square root? Where did that come from? I think it came from hunger. Okay, inverse sine of x plus c. Yep, that's all she got. Okay, can I last 25 minutes? I hope so. Man, I'm hungry. All right. All right, to erase that one? Okay, let's move to example 2. This time we're doing the integral of square root of 1 minus x squared dx. Yeah. Where would you begin on this one? I wish I hadn't erased. Say again? Yeah, yeah, that's why let x equal sine theta. And what were your next steps? Dx is equal to cosine theta d theta. And we can just go straight to the chase here. The square root of 1 minus x squared would be cosine theta, especially if we kept it between minus pi halves and pi halves. Then I think we're ready to go. This integral would now be say again? Squared, cosine squared theta d theta. Okay? And that integral we did in the last section. Look it up. Okay? And that is your half angle, is where you want to go with that. But rather than recreate the half angle thing, unless you just happen to remember it, just look it up and see. Turn back a couple pages, you got it right there in front of you. And that happens to be, and there's a couple ways to express it, and here's the first way, is 1/2 theta, writing it the way they do, plus 1/2 sine theta cosine theta, plus c. All right. Then, oh man, we got to go back, so probably a good idea to go back here too. What would that suggest? Theta is equal to inverse sine of x. Okay, so this will be 1/2 the inverse sine of x, plus 1/2 okay, sine of the inverse sine of x. The sine of an inverse sine is, they wipe each other out. I mean, that's just a finger in the air. Okay? You just get back to where you started. Okay? So that would be sine of an inverse sine of x would be x. So that would be a 1/2 x. But here we have a cosine theta. So that's a cosine of an inverse sine. That's something I don't like to deal with much. Now here's something we haven't gotten there yet, and I want to get there, but we haven't needed it yet. Here's where I say draw a picture. Okay? And here's the picture that I would suggest drawing. Drawing any old angle here, usually in the first quadrant. Make sure it's a right triangle. Let this be your theta. And if that's theta, then what is sine of theta? Opposite over hypotenuse. Well, since we only have one thing there, like x, why don't let that be x, this be 1? Wouldn't that be x over 1? Okay. Now that same theta, well, wait, before we do that, what would this side be? We're going to get there, but what would this side be? If you know this is a right angle, this is x, that's 1, what's this leg down here? the square root of 1 minus x squared. Is that what you said? That's it exactly, isn't it? So your cosine theta is then square root of 1 minus x squared. There is your answer. Okay? Now the interesting thing is, this 1 minus x squared is what you started with up there. Okay? And that is your cosine theta, so you just plug that in for it. Duh. Interesting. So their final answer is 1/2 inverse sine of x plus 1/2 x square root of 1 minus x squared plus c. I'm so hungry I can hardly think. Okay. Let's see what the next slide is. Yeah, that's the right one. I thought we were just about caught up with the two additions. We're back on kind of the same page now. I hate to do this, but I think I need to run down the hall, at least get something to drink. I mean, just a swig of water or something. So, y'all need a bladder break or anything? For a department chair. Okay. I forgot to turn on the thing. Okay. As soon as it comes up, we'll see the little box in the book. Sorry, I should have turned that on first. Okay. When you have integrals involving a squared minus x squared, now so far we just have one, but it works this way too. If the square root of a squared minus x squared is anywhere in your problem, it occurs in an integral as long as that a is greater than 0. Okay? It's going to be hard to tell because all you're going to have is a squared, and that's, you can't tell if a is greater than 0, but this requires a to be greater than 0. Try the substitution x equal a sine theta. Then immediately you'll do the dx is equal to a cosine theta d theta. By using sine, then you avoid the minus there. Okay, so that works nicely. And then when you plug back in, you see that the square root of a squared plus minus sine x squared is a cosine theta again, because you plug this in there and you get it. So everything you have, this becomes a cosine theta. This is a cosine theta, a cosine theta d theta. So either things are going to cancel out, or they're going to combine together, or something, and you can usually solve the problem from there. Okay. Now, jumping another rabbit here. I used that phrase in my last class. There we go. I hit that key before and it did the same thing. All right. Here is, we're going to use this figure on this problem. And by the way, get used to the triangles. They really are helpful. Okay? Here's what our problem is. We're wanting to integrate x squared over 4 minus x squared raised to the 3/2 power dx. Okay? Now, if that were an x up here, not an x squared, a simple substitution is going to take you to time. You'll be fine. However, it's not. That's an x squared up there. So there's not much we can do with the simple substitution. So since this is a form, looks like, and this is a radical, even though it's in the 3rd power, don't worry. I think that's still going to be to our advantage. So what might we try?
X is equal to
Let x equal, you do have this constant here, so what do we do with it? Okay, square root of, yeah, 2 sine theta. Okay, then, a bunch of thens here. Dx is equal to 2 cosine theta d theta. Can we go straight to the radical, or do we need a couple more steps? Huh? Square root of 4 minus x squared will be 2 cosine theta. Exactly. Okay. I think that's all we need for now. Okay. So let's do the substitution. Say that again. 4. Yes, okay. You're doing it right. I was going to say we have to do the x squared there, but you did it. Okay. 4 sine squared theta. Second. Okay. Over. 2 cosine theta, the whole entity there cubed. Okay. Be careful how you say it, that you get the concept right. Okay. And then the dx is what? It's what? 2 cosine theta d theta. All right. Lots of numbers in here, but if you'll notice, you got 4 times 2 in the numerator-ish, right? And 2 cubed in the denominator. They all cancel out. The numbers do. Okay? So let's go on and get rid of them. Okay? Okay. Notice the sound effects. Okay. Now, the cosine is still cubed. We took care of 2 cubed, but, you know, all right. What does this form result in becoming? Sine squared theta over, okay, except you got a cosine theta up here too. Okay, d theta. Well, what's that? That's the tangent squared theta. And guess what? From the last section, I think we had, or a table, we had what that was. I want to make sure I'm not leading you down a bad path here. Yeah. Now, we don't have to go back and find it. The book suggested a very good way. If you see tangent squared theta and think Pythagorean identity, what's that? Okay, let's try that. Be the integral of 1 minus secant. Wait. Yeah. Wait, that's not right. Secant squared. Yeah. Secant squared minus 1. Okay. Okay. Anyone know what the antiderivative of secant squared theta is? as tangent theta, right? How about 1? Theta. Perfect. There we have our integral. Okay. And I guess we need a plus c here, but we need to get back to our x's. Okay? And this is where the triangle comes into play. Thank you very much. If you remember that sine of theta is opposite over hypotenuse. That makes the opposite side the x and the hypotenuse 2 for that angle theta. Okay? And by the way, then this side over here becomes the square root of 4 minus x squared. That was your cosine theta. Well, wait, not quite. No, it's the Pythagorean theorem. 4 minus x squared is square root of that. Yeah. So that's what's under there. But what we want to know is what tangent theta is. And what is tangent theta then? Over adjacent to right. So there we have that answer from our triangle. See, I said the triangle will be very helpful to you. X over the square root of 4 minus x squared. Okay? Minus, now, what is theta? There you have to go back to your original substitution. And what was the theta? Yeah, it's the inverse sine of x over 2. Yeah, minus the inverse sine of x over 2 plus c. That is your answer. Okay, the x over the square root of 4 minus x squared minus inverse sine of x over 2 plus c. Okay. Now, did y'all need that any longer? I'll erase it pretty quickly. But I didn't erase it, but I can go back to it. I need to find my cursor. Where have you gone? Well, I don't know. How do I get out of this? There we go. Now, what if we had a form of the middle one we had? X squared plus a squared. What does that look like? Tangent, because tangent squared plus hypotenuse 1 is secant squared. So that's what I would do. Try that. If that occurs anywhere in your integral, okay, then try x is equal to a tangent theta. Tangent theta is equal to x over a. Okay? Draw your little diagram, your triangle as well. Take your dx here. What's the dx of this? D of this? Secant squared. Yeah, a secant squared theta d theta. Okay? Now, they just sort of pop that on you. Let's think it through. Okay? Square this, a squared tangent squared theta, plus a squared. So you can factor out an a squared and take it out of the radical, and that gives you a. And then you have a tangent squared theta plus 1. And that's secant squared theta. Take that out of the integral and you get secant theta. So, sure enough, that does give you that. Now, the other way you get there, that's one way to get there. The other way you get there is with your triangle. And they came up with a triangle right then. This is for the next problem. Let's go back and do the triangle here. Okay? If you make your own triangle, you don't have to wait till them do it. If this is your theta, and you're dealing with tangent theta. Tangent theta is opposite x over adjacent a, and that makes the hypotenuse the square root of a squared plus x squared, right? Or x squared plus a squared. Doesn't matter what order you do it. And then the relationship between hypotenuse over adjacent is secant, right? Because adjacent over hypotenuse is cosine, hypotenuse over adjacent is secant theta, then multiply both sides by the a, and you get a secant theta is equal to the square root of x squared plus a squared, or a squared plus a squared. Okay, so your picture can show you that as well, or you can start playing with the numbers. Either way, whatever way you see or understand or want to go best. Okay, so with that in mind, let's do, hey, no problem. I do have some, but some of these are you already rated these?
Yeah, last.
Oh, okay, and they didn't work. Okay, yeah, I've got some down in my office. They're hanging in the bag right behind the door, I think. So let me give you the key. On the doorknob just inside the office. If they're not there, I don't know where to tell you to look. That's where the word's on. I think there's still something.
We'll be needing a lot of them.
Yeah, okay, yeah. I've seen your boards, so I know what you mean. Okay. I'll erase this for now because, wait, I think the next slide has it. Okay, let's just go to that. Evaluate this. The integral. Oh, man, we're out of time. If he hadn't come in, I think we could have gotten it done. So we'll start next time with example 4. Okay? Let's see how many homework exercises we can do here. I think you can do number 1. Five. 7. Wait, maybe not 7. You can do a few of those. You can pick and choose. Don't do any that confuse that we haven't gotten to yet. But those that use the sign substitutions, you can do any of those odds. Okay? And we'll come back and finish those next time. Okay? Good deal. Sorry we ran out of time. Sorry I had to take a break.